Hello.
Hello,
Professor.
Let's bring it back to the 1890s.
I'll go back. Video 9, organic reactions. There's a pogo for this.
Yes.
Also, so we got to be able to read and recognize some of these reactions just by what we see as products and reactants.
7 of them total.
7 of them. Let's see if we can get through this in 10 minutes. First one, the greatest of the reactions, right?
Combustion.
Fire.
Yeah.
So we need methane in this case. We need a hydrocarbon. You can see in the writing, right? Always in the presence of
Oxygen.
got to have oxygen. That's part of that fire triangle, right? And the spark hits, and I always produce carbon dioxide and water. This is a guaranteed thing.
Absolutely, every time. So you know you've got combustion by seeing the 2 products of carbon dioxide and water, and the 2 reactants is a hydrocarbon. It doesn't have to be CH4.
Nope.
It might be something more complex. But that and oxygen makes CO2 and water.
Yeah, so the oxygen, the CO2, and the water are the 3 main pieces that we see there.
Oh.
So we have the hydrocarbon.
Pink
That
binds with oxygen.
Pink,
Pink.
forming,
Carbon dioxide.
and
Water. I recognize a combustion
that
reaction.
is a combustion reaction. Every time.
Memorize these
See, it
reactions.
says right there, must know this reaction cold. Absolutely.
Even though it produces hot.
You're so funny, mister.
Looking.
Okay, addition reaction. Go.
So when you are adding typically halogens to a double bond, okay, so we've got C2H4, that's ethene, and we're combining it with a bromine element, Br2, and we're going to make a halocarbon, C2H4Br2, typically is our product. So
one larger product being the key.
Yep, exactly. So this is a synthesis. So you get an alkene or an alkyne. You got to have a double or a triple bond in your hydrocarbon chain in order for this to work. For other reasons that we don't get into.
And I told my class, when you draw these out, it looks like there's empty parking spots.
Yeah, that's a good way to look at it, right? So you combine that with a halogen and you get a halocarbon. So there is some type of halogen, bromine, chlorine, iodine, fluorine on that molecule. And this, what you see down below, is definitely a step-by-step mechanism of how a bromine atom gets added, or 2 in this case, gets added into the hydrocarbon chain, where that double bond breaks and forms and catches the bromine atoms that are coming from the bromine element to make the halocarbon. And
you can see that empty parking spot that bromine's going to go and park right into.
If you go to college and study organic chemistry, like a major portion of your curriculum will be studying simple addition reactions just like this.
So one product is key here. One product, and I'm just simply adding those halogens onto the hydrocarbon.
Both of them.
Correct.
Now this with the substitution, it looks a lot like an addition.
But it's a little different.
It's a little different because you start with a hydrocarbon, C2H6.
Except for now we are saturated, so it's specifically an alkane, and that follows my N2N plus 2. Right?
And we're going to add bromine, but we're only going to add one of the bromine atoms. And the other bromine atom teams up with the hydrogen that it kicked out to make hydrobromic acid.
So essentially one hydrogen and one bromine atom literally switch, and that's why we call it substitution.
Right. So one hydrogen swaps for a halogen.
Right. So we always start with an alkane.
Yep.
Specifically an alkane. It's got to be single bonded. Then I take that diatomic halogen.
Chlorine, bromine, iodine, fluorine.
Yep. And then I'm going to make this halocarbon with an acid.
Mm-hmm.
And then here's this picture. And you're going to see this picture looks very similar to the other, except for literally we just take a Cl and an H and swap them.
And there's 2 products.
Yeah. So that way we can see the difference.
Mm-hmm. So there's no mechanism here, but it took a hydrogen off and added a chlorine on.
There's the substitution it is. It's not just a straight addition, it's a substitution. Now, esterification means I'm going to make an ester.
Right.
Okay. And it just so happens to be a dehydration. Polymerization, and we'll see that. So I'm going to take this organic acid. I see the coup.
This is acetic acid in this case.
Yep. And then I'm going to take an alcohol. It's got an OH functional group.
Ethanol in this case.
Yep. And I'm going to, of course, make now an ester.
Yep.
And water. And real quick, before we go anywhere, I'm going to show you real quick. Hydrogen loses an H, and alcohol loses an OH, and that's where I get the water from.
Right. That's why it's dehydration, because it produces water which you then can remove.
Right. I'm like pulling water out of it.
Mhm.
So it's dehydration.
Now, so there's your organic acid. It could be any one. This is the simplest one. And then you have to combine it with an alcohol. It could be any alcohol. This
Yep.
is not the simplest, but pretty simple.
Yep.
You're always going to make an ester and water. And now I personally think that you need to see the visual structures, because you can't tell that C2H4O2 was an ester right away. You got to see the functional group,
Right.
which I'm going to circle for you in the
Right.
product.
And I like that this one's color coded, because you can see the OH and the H are blue, that are going to form the dehydration. And then that leaves the C double bonded O and the O over on the other side. And that's where I get that. That's right where it comes together to form that functional group.
And what he's explaining is what R means, R and R prime. They're just hydrocarbon change. 1, 2, 10, a
Any
billion. It
That's
could be
written right in the
anything.
reference table. R is any number of carbons.
Hydrocarbon chain.
Right. But specifically now, what you did right, so let me do blue. This part of the functional group hooks on with this part, and that's what makes
Right.
that part.
Absolutely. So esterification is kind of complex, to be honest.
It really is.
And it's pretty rare, too.
It is pretty rare. We do need to know esterification makes esters, of course,
Mhm.
and that's how.
Yes.
Okay.
Now, saponification, this one's cool. It is an ester. So let's say we made an ester.
Right? Or any fat, even.
Any fat, triglycerides are fats. This is oil. Okay. Esters, oils are esters.
Yep.
Okay. You combine it with a base,
Very strong base.
extremely strong base like sodium hydroxide, and you make a soap molecule and a glycerol molecule. So if you can imagine, 100,000 years ago, cavemen are sitting around a fire grilling their meat. That mammoth fat drips into the ashes under the fire and becomes a soap, because the ashes are strongly basic in a fire. Becomes a soap. Weather system rolls through and the rain falls down and gets all bubbly and soapy and sudsy feeling. These cavemen are like, wow,
Yeah.
it actually takes the dirt off my hand.
Yeah.
The genesis
I
of
think I
soap.
learned about it a lot with like near the Nile River, and
Oh.
some of the things they were doing with human.
Remains.
Yeah.
Wow.
And what it was doing to the water, and then
Right.
they would go in the water and get cleaned up.
Wow.
So that's how I learned about it.
And then I
That's
heard
that's a good one.
Old time, old times they would kill a cow, and part of the whole
Yep.
harvest cycle was you kill the cow, you render the fat, you make the soap, you eat the meat.
Okay. So here's the other one, know it cold. So this is the other big one that honestly is probably the second most common one you're going to see.
Fermentation.
I'm going to take sugar,
Mhm.
and in this case, this is regular sucrose, right?
Glucose.
Glucose. I mean, yep.
Yeah.
I'm going to hit it with an enzyme.
Yep.
And that is literally going to make an alcohol,
And
carbon dioxide, little bubblies in the alcohol.
Right.
See the OH group that is an alcohol, and I balance the equation properly so nobody can get mad at me.
Mhm.
So sugar,
Yep.
plus
Using-
enzyme
Enzyme as a catalyst.
as a catalyst produces alcohol.
and
Carbon
carbon
dioxide.
dioxide.
So producing alcohol is fermentation,
Mhm.
and we just showed you the reaction.
Yep. Typically, the only type we ever see this is the production of ethanol, not methanol. So
Correct.
sugar makes ethanol and carbon dioxide when the enzyme comes in contact
Yep.
to it.
Good. Oh, we one more. So
Polymerization. This one, there isn't much to write because they're complex.
yeah, we really didn't write anything in here. We'll just talk you through a little bit.
We basically need you to understand that if you take a bunch of small molecules, you can do chemistry.
That's these guys.
Yep. Those are all the monomer units. If you take a bunch of those and do the right chemistry to them, you can link them together to make a bigger, longer chain.
Yes.
So you take ethylene in the case of Mr. Milk's circle, and you combine them through the right steps of reaction polymerization. You get polyethylene,
Many ethylenes,
which is
literally
essentially styrofoam. And
right.
the great thing about polymerizations is that you can have almost unlimited different possibilities. You can
True.
tailor your reactions a certain way.
Right. And what's also cool about them is they are very easily controlled
Mhm.
with temperature and time and pressure. And, those
And they
things. You can
definitely
really
need-
control them.
I mean, I'll circle it right here. You need heat, pressure, catalysts. Those are very important
Yep.
to make polymerization happen. And in polymerization notation, these ellipses, the dots, are
Means
very important.
any number.
And it just continues and
Just
continues
keeps
and
going
continues.
and going and going.
And for that reason, N also means, so these
Some
brackets
number.
with N, how many on one side?
Any number.
N. It just
You know what's
continues.
nice about this video? It's not going to keep just continuing and going on and on, because guess what?
We're done.
It's over.
We're done with the unit.
Say it one last time.
That's all, folks.
See it.
See it.